50 years ago, it took more than 1.5 minutes to connect a call. Today, it takes 1.5 seconds, a drop of more than 99%.
Almost every aspect of telecommunications is a queue. And in fact, queuing theory was invented to understand problems in telecommunications.
More than 100 years ago, communication was revolutionized by the telephone. Using a telephone, people could send their voices through a thin wire. The call was then routed by an operator. Long-distance calls were routed to other operators who routed calls across the country. At each location, a call would have to wait in line to be served. And having enough operators ensured a short wait. To ensure quick connections today, the AT&T network provides 134 possible routes for every call. For example, if you make a call from Boston to Miami, the call might be routed to any of 134 possible locations where the network is less busy before reaching its final destination. As demand on the system continues to increase, the system grows. And that's where Massey comes in. Massey's job is to develop mathematics that predicts how quickly the network should grow to ensure quick and inexpensive service. When he works on the phone system, he reduces its complexity to its essential elements. This is an important mathematical procedure called making an abstract model.
In a sense, what abstraction does is that you're taking a complicated object and boiling it down to some essential quality.
To Massey, an abstract model of the phone systems looks like this. Telephones are connected by wires called a local loop. When a call is made, a signal travels along the local loop and goes to what is called a central office. From the central office, the call travels along something called a trunk line. Trunk lines link central offices. Once a call reaches the appropriate central office, the call is routed to its final destination. What mathematicians like Massey try to figure out is how many trunk lines are needed on the system. Too few trunk lines and the system is slow and sluggish. Too many trunk lines makes for an inefficient system, which is costly. Next, Massey captures the complexity of this system using a mathematical model. The models contain variables like the number of trunk lines, the lengths of calls, and call completion rates. Using equations like this, Massey can build and rebuild extensions to the system until he creates one that runs cost-effectively.
The thing to remember about mathematics is that it's mostly about symbols. So manipulating symbols which can stand for other things that are much larger than themselves.
The mathematician looks at the symbols and sees what those symbols represent. They see the beauty behind those symbols. It's a bit like looking at music. If you're trained to read music, you can look at a piece of sheet music and you can hear a symphony playing. If you're a mathematician, you can look at a page of symbols and in your head you hear a mathematical symphony playing.
Mathematical notation is a common language shared by all mathematicians. Mathematical inspiration, on the other hand, is a personal thing.
I am very curious about everything, and so it's very important for me to know the truth about things. And so I have structured my life in order to find out the truth. I use martial arts to uncover things about myself and what's going on inside of me, inside my head. In my mind, part of exploring is searching and recording information. So photography records information. They're sort of like a different type of truth, a different type of understanding that I achieve there.
Nate Dean uses martial arts and photography as a way of making sense of the information age. He also relies on the power of mathematics. Dean is a data miner who sifts through the information age clutter in a search for useful and meaningful patterns.
We're certainly collecting more and storing more information. And I guess more and more now people have realized just how important this data can be. People store data in lots of places, supermarkets, banks, companies, schools, libraries, all kinds of industries sort of collect information about people or events. And in data mining, what we try to do is somehow extract essential details or information from that data.
Today, data mining is used to look for patterns in the stock market. Data mining is used to find patterns in statistical data and satellite information. Much of Dean's work involves cellular telephone fraud. He develops mathematical tools that can be used to look for patterns in your phone bill. For example, your cellular phone bill clearly shows your calling pattern. Dean develops software that detects dramatic changes in that pattern. A dramatic change may indicate that someone has stolen your cellular code